I'm starting with a little bit of a different view here today. I'm looking inside of GeoGebra and I have three columns representing three different types of flowers and how long it takes me to knead bread using these different types of flowers. So A is Arthur's flour, B is Bob's Red Mill, and C is Ka Smart. And I'm trying to save time when I'm making bread, so I'm looking for the best possible option. And a question that sort of came to me is there a difference on average for the amount of time that it takes me to knead the bread? So what I've done is I've typed in all of the minutes that it takes. I've highlighted the data here in GeoGebra, and up at the top, I've selected the option for multiple variable analysis. And what this has done is it's given me the stack box plot. And I can see here is Arthur's flower. It looks like it might be the shortest amount of time on average, except I have this line up here for that maximum. So it's possible that it takes a long time compared to some of this Bob's Red Mill flower. So it's not consistently the shortest. Sometimes it's longer than some of these other brands. So I can see maybe on average it's faster, but I'm not convinced yet. And I want a model and a statistical analysis that will actually allow me to look at this in more detail so I can see what's going on. I'm going to add just a tiny bit more to this table. I'm adding to the bottom, I now have the means and the standard deviations for each of those groups. Means are my X bars, my standard deviations are the S's, and I'm going to write this down in my main packet. This is the first page of lesson 12, day 1, or at least part 1, of a lesson on analysis of variation. And I'm going to move to that analysis of variation packet now. So I'm going to switch to view. This tends to cycle through my face like 3 or 4 times before it actually ends up going to the overhead. So hang in there with me. Great. Okay. So first off, I'm going to be analyzing a couple of different types of spreads or variation. So I'm looking at an analysis of variation, taking the first letter or two from each of those words, forms an acronym, Anova. So Anova will be measuring a lot of different types of spreads and trying to see if there's a difference in averages. So here I have my 3 flower amounts written down again, and I've calculated those averages and standard deviations on the side. To find the averages, I add up all the values and I divide by the number of samples. I'm going to calculate another average to kind of compare it to this. I'm just wondering in general how much time it took me to knead bread. So I'm going to make this a capital X bar representing all of the bread here. I'm going to start at 20 plus 30 plus ... all the way up to the last value in my list here is 37, treating this as like one mondo list instead of 3 mini lists. If I do that, counting out my values, it looks like I have 34 numbers. Typing that in my calculator, and I cheated a little bit, I already have it typed in my calculator, so I just had to hit enter. I'll do so now. Great. I get approximately 30.44 minutes on average for everything. Units on all of these things equals minutes. And the reason why this average is nice is I can kind of compare each of these base averages to my overall average. And I can ask myself, is 24.8 close or not close to this 30.44? Well, what about that 29.42? Is that close or not close? That looks reasonably close. 36 looks like it's pretty far away. And the only reason why I know it's pretty far away is I'm considering how many standard deviations it would take to get over there. It seems like it would take about 3 standard deviations to hit that 36. That seems like it's an unusual distance away. So I'm already kind of starting to think in the way that I'll need to later on in the lesson In some sense, I'm comparing each of these individual averages to an overall average, but I also want to take into account the size of each of the individual spreads. I'm going to go over this in a lot of detail today, and this is again a two-part lesson. So for the most part, I'm just going to be doing this one example in a lot of detail to try to figure out what the heck is going on. I'm going to review how to calculate a standard deviation. More specifically, I'm going to calculate the variance first. The variance is the standard deviation squared. And I just want to show you the setup for what that would look like if I was trying to find the variance for Arthur's bread by hand. So the process here is I add, remember this symbol means add, the values that I care about minus the center. This gives me a gap. I square it so I don't get zeros. This is a lot like chi-squared, where I have observed minus expected. Average is expected. These are my observed individual values minus the expected. I'm squaring it. And I'm dividing this by the total number of gaps. This n minus 1 should look kind of familiar. This also showed up a lot as my degree of freedom. So for this calculation, I had 20 minus my average for A was 24.8. I add all of those up. I counted out the number of bread. I had 10 types of bread that I made using Arthur's flour. 10 minus 1 gives me a denominator of 9. When I did this division, I ended up getting something like 9.734 or so. Finally, if I wanted my standard deviation, I took the square root of that variance, and this gave me approximately 3.12. So if you're trying to figure out where that 3.12 came from, I'm just showing you that again from Math 243. This was that setup for finding the variance. Follow-up question, does there appear to be a difference in bread? So to me, this sounds a bit like a test question in that there seems to be an implied null hypothesis. There is no difference on average. In an alternative hypothesis, at least one average is different. And again, I'm seeing that this kind of has that chi-squared flair to it, where chi-squared, my null hypothesis was sometimes that p was equal to different proportions, and the alternative hypothesis was at least one of those proportions was different. And when I looked at those stacked box plots, I had something kind of sort of like this. I'm not a very good artist. And it kind of looks like there is a difference in those averages there. So yes, at least I think so. And here's the reason why I think so. This one block seems to miss all of the other blocks there. So we're just going to practice looking at a couple of these stacked box plots and try to determine when it looks like there's a difference and when it doesn't look like there's a difference. And I'm going to use all these numbers again, so I'm keeping this page close by. So which of the following scenarios appear to have a difference in averages? So scenario A, suppose I have 3 different groups and it looks something like this. Scenario B, I have something like this. And in scenario C, I have something like this. These look like little TIE fighters to me. Okay, I just want to make a note. In both A and B, my centers for these groups seem to be lining up. However, in A, when I'm looking at this, I would say that these three groups appear to miss each other. So I think that these have different averages. Now, the interesting thing is I have the same averages here, so it's not enough for me to just say these have different centers. These have different centers too. I also have to consider the fact that these groups have overlap, while these had different centers and these had no overlap. So in a situation like this where it clearly misses, I would say this looks like, yes, it looks like there's a difference in average. They clearly miss. Here, not so sure. Maybe not, because there is so much overlap between those groups. So A looked like different. B, maybe not actually different. C. Now this one's interesting because I just have this one group hanging off by itself. I have a lot of the averages are the same, but if I have at least one average that is different, then for the stuff we're doing today, I'm going to want to reject that null hypothesis, and I'm going to have evidence that not all of the groups are the same. In fact, if I were to look at sort of a middle line here, kind of going through all of these values, this middle line being the average of all of these averages, this capital X bar, I would see that a lot of my groups tend to miss that capital X bar line. In contrast, if I put my capital X bar line on this, the average of my averages, it tends to go through all of those boxes. It seems like they could be the same. If I averaged out all of my values and put that capital X bar line on this, it's missing some of those blocks. So this capital X bar, this is the average of all those values. This seems important for trying to determine which groups look the same and which groups look different. So two observations, and then these two observations are going to become two different types of variances that we calculate here. First observation, we need to compare the centers of the distributions. If all of my boxes line up perfectly in the middle, there's no reason to do a test. I don't have evidence of a difference. So I have to have different centers for me to have a reason to even want to analyze this thing in the first place. So I'm going to compare all of these individual X bars for each of the group to the overall middle line, that middle line being capital X bar. So what I'm going to do here is I'm going to see how much variation is there between my groups. Does it kind of fall through the middle of everything, or does it miss some things? How much variation am I seeing between my different little TIE fighter box plots? Second thing, and this has to do with either being inside or not inside, has something to do with the overlap in the size of the boxes. So I need to compare the spread of the data sets. And the way I compare spread of the data sets is I look at the standard deviation of each set, and that will tell me something about how big that box is. So this has to do with comparing the centers of the boxes. This has something to do with the width of the boxes. And both of those components, different centers and overlap, that was important for me telling if things look the same or if things look different. The name I'm going to give to this is the variation based off the size of the boxes. So this is an internal variation, a variation within. So I'm going to compare this variation between groups to this variation within groups. So here's my idea for the next 2 pages. I'm going to come up with a mathematical formula that looks at the variance or the variation between groups. And on the page after, I'm going to come up with the formula that looks at the variance or the variation within the groups. So first type of spread that I'm going to be analyzing here with you, variation between groups. I'm just going to write myself a note here. This is going to compare the centers of the boxes. I'm just giving you a sneak preview before we actually get into the pages. Next page, variation within the groups. This is going to look at the spread of those boxes. And it's going to look at the spread using those standard deviations. Again, I'm going to go over this in a lot of detail on each of these pages, but I'm just telling you what's coming up. So that way, as we're going through some of these longer calculations and you're wondering, well, what's the point of all this? Well, I want to have 2 different numbers and I want to see if these things are close to each other or not close to each other. Ultimately, I'm trying to figure out how close to this middle line am I? Am I missing it entirely, or does it have a little bit of overlap? So let's start by comparing centers. And my goal here is to find a variance. And variance is going to be I'm adding the values that I want to compare minus the center of the values. I'm going to square these things so I don't get 0. And I'm going to divide it by the degree of freedom for the thing I care about. So as a reminder, on this page, I am comparing the centers. So it might help to actually have those center values again. So my values I'm going to be comparing. These were my 3 averages. My 3 averages were 24.8, 29.42, and 36.17. I need something to compare these to. And when I was drawing these pictures, I had all these different centers that I was comparing. And the thing I wanted to compare them to was this line that went through everything. That line that went through everything was my capital X bar. It was the value, average of my values. In some ways, this is kind of the average of my averages. So for my center, I'm going to have my capital X bar. This is my average of all of those numbers. This is what happens if I pool together my data. So I'm going to set up the variance by comparing these two things. And my capital X bar, as a reminder, for this particular data set was 30.44. Let's give it a go. My variation between groups, I'm going to take, and I'm giving myself plenty of room. I'm trying something new. I might make a mistake because I'm trying something new. That's okay. It's part of a process. I'm going to take the first value, 24.8. That's my X bar VA. And I'm going to take value, first value, minus the center of all of those things, 30.44. And I'm going to square this already because I saw a negative show up and I don't want to end up getting 0. Next value, 29.42 minus 30.44. I'm squaring this so I don't end up with 0. Last value, I have 36.17 minus 30.44, and I'm squaring that so I don't end up with 0. I had 3 groups that I was comparing here, A, B, and C. So if I'm talking about my degree of freedom, well, that should be 3 minus 1. So my denominator, this looks like it's the number of groups, take away 1. This is a really good first draft. In fact, this is almost exactly what I want. There's only one small problem. Right now, this is saying all 3 groups are equally important to me and I want to weight them the same. But when I look back at the data set, I noticed that I had way more samples in the B and C group than I did in the A group. So I should probably weight each of these things by how important they are. So instead of taking this as is, I'm going to add a value here, 10. That's the number of samples for the first group. I'm going to weight this by how important it is. The next one, that showed up 12 times. That's the weight. And last one, 12. So the first one was 10 important. The second one was 12 important. And the third one was 12 important. Typing this into my calculator, I get a variation between the groups of 362.29. Let's write out the formula for this thing and label everything inside of this formula so we can make sense of what's going on. The variation between groups. I added a whole bunch of spread. The symbol just means add. I took all of my sample sizes. These sample sizes were the weights. They told me how important each of those spreads were going to be. I took each of the individual averages. I'm using I for individual. So this is the first N paired up with the first average, the second N paired up with the second average, and so on. I for each of the individual groups. So I did my individual averages, and I subtract from that the center line. That center line was this capital X bar. This was the overall average. So I'm doing value minus center. I'm squaring this so I don't get 0. And I divide this by my degree of freedom. My number of groups minus 1, k minus 1 is my degree of freedom for the variance between groups. I'm going to write out this formula again. My variation between groups is equal to the sum, number of samples, times X bar I, my individual averages, minus capital X bar squared, average of all of my values divided by k minus 1. The number of groups minus 1 will give me the degree of freedom for the number of groups. So this has a df of k minus 1. Whatever the denominator is, that's my degree of freedom. Our variation for this first set between the groups for the branch of flower was 362.29. And this was with a degree of freedom of 2. 3 groups minus 1 gave me 2. This was the variation from the centers. You can think of this as the variation that your data has taken up just by comparing the groups. I need something to compare this to because 362, if this was a z-score, I'd be like, dang, that's a massive z-score. But I don't have a reference frame until I consider how big my boxes can be with respect to this amount of variation that I've taken. So let's look at the variation within. And the variation within groups, this is going to look at the spreads, and the spreads are my standard deviations. My standard deviations, just to get these down again, 2.12, 3.12. My standard deviation for the B group was 2.87. So I want to end up with a variance that looks at all of this inside variation between the groups. So variation within, I'm going to take all of this spread based off the size of the boxes, and I'm going to see if I can combine this together. So here's my idea. I'm going to take each of these individual variances, 3.12 squared. My second variance is 2.87 squared. My last variance is 2.12 squared. And I want to average this based off the total number of values. Now, like before, if I said this is worth 1, this is worth 1, and this is worth 1, my weights wouldn't work. Reminder, I need to have weights for how important each of the groups are. In this case, I'm going to weight each of these things by their degree of freedom. And I'm going to see what I get for the top there. So I have 9 as the first degree of freedom times 3.1 squared. Second one is 11 times 2.87 squared. Last one is 11 times 2.12 squared. If you're wondering, well, why the heck am I multiplying by the degrees of freedom here instead of just the sample size? I just want to look back at something from this first page. What I'm really trying to do is I'm trying to get all of these individual variations of values minus center squared. So I'm actually trying to cancel out each of these denominators for each of these fractions that I would have when I'm looking at those variants. Because I want to look at the total amount of spread within my data set comparing my values to their centers. The problem here is I have 9, I have 11, I have 11. I want to average these things out. So on the bottom, I'm going to have the total for the degree of freedom. So I'm going to have 9 plus 11 plus 11. I believe that's 31. I'm going to type this into a calculator and I'm going to see what I get. I appear to get something like 7.34. And this tells me something about how wide the blocks are. Now this one I can actually make a little bit of sense of. This is the variation within my group. And I'm going to keep this thing and I'm going to write a formula for it. But just a quick little side note here. Let's take the square root of this variance to get a standard deviation. So I'm going to take the square root of 7.34 and let's see what this gives me. Now here was my goal for looking at this variation within, is I wanted to take all these standard deviations and kind of pool or average them out. So I'm seeing some things are in like 2s, some things are in like 3s. I'm hoping that if I average or pool these things out, I'm going to get something like a standard deviation of 2.7. In a lot of ways, this is the standard deviation for my entire data set. Let's see what I get if I actually do this. .7, great. So this pooled standard deviation is kind of the standard deviation that's in the middle of everything. Sort of like capital X bar is in the middle of my averages, S pool is kind of in the middle of my standard deviations. Here's the process that we use to find this. The variation within, which is my S pool squared, my pooled variance. I had an addition of a whole bunch of things on the top there. I had each of these degrees of freedom. Each of those individual variances. And I divided this by the total degree of freedom. Now, just as an observation, I started out with going back to this original set of data, 10, 12, 12. I started out with, what is that? 34 values. Now, when I'm combining the degree of freedom, I'm taking away one for each of the groups. So I took away from this 34, one from the first, one from the second, and one from the third. I've subtracted 1 3 times there. So what I've done is I've taken the total number of terms and I subtract from this the number of groups. If you're having a hard time figuring out where this thing comes from, just remember this is the total for those individual degrees of freedoms. I'm going to write this again. My S pool squared, which is my variation within, is the sum of each of my individual weights times those variance for the groups divided by capital N. This is the number of total terms, minus K. This is the number of groups. Every variance has a degree of freedom, and the degree of freedom always lives on the bottom. So my total degree of freedom is capital N minus K. So for our problem, we ended up with a variance within of 7.34. And the number that we used for the division to come up with that 7.34, our total degree of freedom, was 31. A quick double check. We had 34 numbers and we had 3 groups. 34 minus 3 gives us 31. We now have 2 variances, and I want to start to really tie everything together here. And I want to name these things and make sense of them as much as I possibly can. So the variation between groups, this is how much spread we've taken. The variation within groups, this is kind of like the allowance. This is how much spread I was allowed to take. So think of this like your bank account. You have $7.34, and you go out and you spend $362.29. You've spent a little bit more than you were probably supposed to. If you're spending less than that variation within, you're inside of that fair area, you're probably going to fail to reject the null hypothesis. Are you spending way more than you should? That's unfair. That's probably telling you there's a difference in those averages. That's probably going to cause you to reject that null hypothesis. So, the variation between the groups, this is the amount of spread between the centers. You can think of this as sort of the amount of spread that you've used up. The variation within groups, this is the amount of spread we were allowed to take. So if I'm wondering, well, what percentage of the spread did I take? I'm going to find something called an F ratio, and I'm going to take the total amount of variation that I spent, and I'm going to divide this by my allowance, the total amount of variation I was allowed to take, the variation within. So for our values, I was allowed 7.34, and I was like, got it, I'm not going to spend more than 7.34, but then I went out and I spent 362.29. So I'm going to write this thing and figure out sort of what's going on percentage-wise. Okay, probably not great for my finances. I end up with 49.36 or so. If you're thinking, well, you're only 49% off your budget, careful with your decimals. So if I actually think about what this means, well, 1 is 100, so I'm really 4,936% off of my budget. I am off by a considerable amount. So you can think of F as roughly being the amount or percentage of allowed variation taken by the difference. I've taken a ridiculous percentage of that variation. This is probably an unreasonable amount. It's probably too large. What I'd like to be able to do with this F, though, is come up with the p-value by doing some sort of FCDF nonsense, in the same way that I had a t-CDF to do t-score stuff and a chi-squared CDF to do chi-squared stuff. Now, before I can do anything in my calculator, though, I need to know which way to shade. This page is going to look remarkably familiar if you recently looked at that lesson on chi-squared, because it's going to follow a lot of the same guiding principles. I'm going to try to figure out what it looks like for this F ratio. If I have really similar groups, I'm going to look at what's happening to this F ratio if I have very different groups. And I'm going to see which way I shade in both. So 2 what ifs. First what if. Let's assume that the average of all of my groups is really, really similar. So in this case, I'm thinking of my TIE fighter picture. Let's assume that my TIE fighters pretty much line up perfectly. So if I looked at the variation between the groups here, well, there is no variation between those groups. That's pretty dang close to 0. So my variation between the groups is going to be really small when those groups look similar. Now this variation between, this is the top of a fraction. So if I have something like 0 over 10, well, 0 over 10 is going to give me 0, so having something small on the top causes my fraction to be small. The smallest my fraction can ever be is 0, but a small F score is going to be close to the start of that mound. Let's say a small f might be somewhere about here. Now I want to know if I should be shading to the left of my f-score or to the right of my f-score. And to figure out which way to shade, I need to think about the conclusion. In this what if, I have assumed that my averages are very similar. So I don't want to say that anything is different because they don't look different at all. I want to fail to reject the null hypothesis. In order to fail to reject the null hypothesis, though, I need to have a large p-value, because small p-value, the null must go. So I have to figure out if I'm supposed to shade left or shade right, and I just have to keep in mind that I'm looking for the largest part possible. If I shade to the left, that looks like a pretty small slice, but if I shade to the right, that's the winner. That looks like a pretty large p-value there. So in the situation where it's fair, just like chi-squared, that was a shade right deal. Let's look at the situation where this is unfair. So I'm assuming now that I have groups that are really spread apart. So when I'm comparing these things, I have a really large variation between my groups. When I'm thinking of my fraction, if I have something like 1 billion, something really large on the top, and I divide this by something small, small like the size of those blocks there, well, 1 billion minus 2 is still a ridiculously large number. So if I have a large numerator, I'm going to have a pretty large fraction. So in the situations where my averages look very different, I'm going to have a large F if it looks unfair. Thinking of this in terms of this hypothesis test, if it's unfair, then I should probably be rejecting the null hypothesis. I'm trying to figure out if I'm supposed to shade left or right on this curve. Well, if I'm supposed to reject the null hypothesis, I need to have a small p-value to do so. Left looks pretty large, that's almost 100% of the curve. Right looks pretty small, I'm going to shade to the right. So if it is unfair, so if it is different, then I'm going to shade right. So if it was fair, I shaded right. If it was not fair, I shaded right. My f-score was 49.36. Observation, just as before, when working with chi-squared, I am always going to shade to the right. So when I do this FCDF business, and I have my low comma my high value is always going to be infinity. It's going to be a right-tailed test. We have so many pieces, and we're oh so close to putting everything together here. So hang on for just one more page as we tie some more loose ends together. We have our test statistic. We have our f-score, or f-statistic. And now we just have to find that p-value. And the way I'm going to do this is using my graphing calculator. So on my TI 83 or 84, I'm going to hit second, vars, and I'm going to choose FCDF. If I'm on a TI-89, I'm going into Apps, Stat List Editor. I'm choosing F5 for distribution, and I'm looking for FCDF. This is in the same spot that you have TCDF. It's the same spot that you have chi-squared CDF. All of these distributions live together in the same location. And when I'm trying to type this into my calculator, the setup is always going to look like this. You have your low value. Your low value is going to be whatever your F-score is, comma infinity, because it's always a right-tailed test, your degree of freedom. At least this is what it was for TCDF and chi-squared CDF. The only problem here, and it's not necessarily a problem, just something we have to be aware of, when we came up with the variation between groups, that had a degree of freedom, but when we came up with the variation within groups, that also had a degree of freedom. So when we say degree of freedom, we need to have the degree of freedom for that numerator. When I say numerator, this is that between groups value, comma, the degree of freedom of your denominator. This was your within. I'm going to write this another way. Our p-value is FCDF. Our F-score that we get by doing our division, comma, infinity, comma, our degree of freedom between the groups was the number of groups minus 1, k minus 1. And the degree of freedom for the second was the total number of terms minus the groups. For our values, we had an F-score of 49.358. It was a right-tailed test, so this was shaded towards infinity. Number of groups minus 1, 3 minus 1 gave me 2. I had 34 values, take away 1 degree of freedom for each of the 3 groups. 34 minus 3 gave me 31 for that second denominator. I'm going to type this into my calculator, and I'm going to see what I get. So second, vars, I'm going into FCDF. My low value, I have 49.358. Large value, I have infinity. I'm just going to town on the 9 button. Degree of freedom for the numerator, that's the between groups, that's 2. Degree of freedom for the denominator, that's the within groups value, that's the 31. Paste and enter. We got 2e minus 10. So this would be 9 point and then 9 zeros after that first decimal point, and then a 2. This is so small that we're just going to call this 0 plus. So let's see what this means. Assuming the null hypothesis that all of the brands of flowers work equally well on average, and the alternative that at least one brand is different, what conclusion can we draw based off of our p-value? Our null hypothesis was the average of Arthur flower was the same as Bob's Red Mill, was the same as Cost Smart. Alternative was at least one average is different. And it won't tell me which one. We got a p-value of, I'm going to write it out, 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros, and then a 2. I regret writing it out. Our p-value is small compared to any alpha level you can reasonably choose. I'm just going to choose a neutral one of 5%. If your p-value is low, the null must go. So we would reject the null hypothesis. If we reject the null hypothesis, we have evidence that at least one average time to knead the bread, prep the bread, is different. So I have evidence that there's a difference in the group. Great. So which group is different? That's where this is kind of a bummer. This doesn't say that group A is different than group B. In fact, if I wanted to know which group was different, I would have to compare A and B. Is Arthur different than Bob's red mill? And I would do this using a 2-sample t-test. I would use 2 independent averages and test to see if those were different. I would also want to check to see if A and C were different. I would also need to check and see if B and C are different. So this test doesn't tell me a lot. It just tells me that something is different in the set of these 3 comparisons, but I don't know if all of these are different, if just one of them is different. I still have a lot of work left to do. So if you're thinking, well, why the heck would I even do this test if I can just compare each group one at a time? Well, let's consider a scenario where I have n, let's make it k for groups. K equals 100 groups. So I have A1, A2, all the way up to 100 different brands of flour. And let's suppose that I did this analysis of variation and I got a p-value of 0.257. I'm just making this up. Is this a large p-value or a small p-value compared to something like 5%? Well, I would probably consider this large. And if it's large, I would fail to reject the null hypothesis. And if I fail to reject the null hypothesis, there's no evidence of a difference. In other words, if I were to do the comparison of A1 first group and second group, first group and third group, and so on, I would expect no difference for any of these comparisons. So how many tests did I just avoid doing by doing Anova to essentially determine if I should do a follow-up or not? Well, in this particular situation, the number of tests that I would be looking at is 4,950. So by doing Anova one test, I can determine if I can skip out on doing 4,950 follow-up tests. Anova is not necessarily useful on its own, but it certainly tells me when I can avoid work. And I'm an inherently lazy person, so when I have the opportunity to skip this much work, I will gladly do so. When Anova tells me, hey, something is different, fine. I'm happy to go through and determine what thing is different now that I know that there's something to look for. Anova essentially works as a red flag. If you reject the null hypothesis, that's a red flag, and you now need to go through and actually do that harder work of figuring out where things go awry. I want to give you this Anova process from start to finish, just so you can see it all together. So, start of Anova, hypotheses. The null hypothesis is going to be that the first average is equal to the second average, all the way up to your kth group. The alternative hypothesis is going to be that at least one average is different. You're going to be comparing 2 types of variation. Variation between your groups. Reminder, this is based off of the centers of your group. And variation within group. This is based off of your standard deviation or the spreads. We calculate our F ratio by dividing the variation between divided by the variation within. I don't know if this is going to help you. This helps me, so I'm just going to share it. This within looks like it's stuck within the fraction. So I remember the within is on the bottom because it's kind of stuck there. These have degrees of freedom. The degrees of freedom live in the denominator, so degree of freedom of k minus 1 and capital N minus k in that order. I do have assumptions for using this model. My assumptions are as follows. Random, independence, large N. This is essentially an average problem, so I need 30 or more samples, or it needs to start normal. And I need to have independent groups. Independent groups tells me that one thing does not affect another. These were all the same assumptions that I had for my t-test. So in a lot of ways, this Anova is an extension of t-test. Now there's one more assumption that kind of we swept underneath the rug as we were going along. And that's something that I sneakily did here. I pooled together the variance to compare the groups. And I found sort of this baseline standard deviation for which to compare all other spreads. And I looked at these things and said, yeah, 2.71 is kind of like those numbers. Now, the only reason why I'm allowed to use this variation within is because all of the spreads are reasonably close. So as an extra assumption, I need to have equal spread. This tells me that my standard deviations are close to one another, that I have roughly the same spreads in the distributions. Here's what I mean by roughly the same. If I had a standard deviation for the first group of 2.5, and for the second group I had a standard deviation of 120.7, I'd be like, okay, that's bad news bears. Those things are crazy different. If I had a standard deviation for the first group of 2.5, and for the second group I had a standard deviation of 3.7, I would be okay with that. So when I say they need to be close, just kind of ballpark close. They don't need to be perfectly the same here. Anova is always a right-tailed test. This is just a quick note on the side. The test name is Anova. The model name is F. So if I ask you what model are you using for this distribution, you're using the F model. If I ask you for the name of the test, you're saying, well, I'm doing an Anova test. I'm doing an analysis of variation. So I do this Anova test by using FCDF, my F score, infinity, my degrees of freedom between the groups, that's k minus 1. The degrees of freedom within the group, that's the total number of terms minus k. I would like to do an example of this with some smaller samples here, just to see what these steps look like in their entirety. So suppose I want to compare the GPA out of 4.0 for daytime versus evening students. So I have daytime GPA average of 2.86, standard deviation of 1.4. I sample 20 students. Evening 3.16. Standard deviation of 1.6, 1.4, and 1.6 are pretty close, so I'll call that good enough. And I'm looking at 30 samples. Use Anova, so use this test to compare the groups. Okay, so let's take a look. Null hypothesis. The average of my daytime students is the same as the average of my evening students. I only have two groups, so for alternative hypothesis, if at least one is different, then that just tells me that two things are different. I had another way of doing this problem before using T distributions. I'm doing this now with F distributions instead. I'm going to do just a little bit of scratch work. Capital X bar. If I had all the individual values, I would add them up and divide by the number of samples. I have 20 samples, I have 30 samples, this is out of 50 samples. When I don't have the number of samples, I need to do a weighted average. Here's how I do a weighted average. I have 20 samples for this first group. The average for the first group was 2.86. So I'm weighting that average by the number of samples. Second group, I have 30 samples and an average of 3.16. I type this into my calculator. I should get something between 2.86 and 3.16. I end up getting 3.04, and that looks pretty good. So to find this capital X bar, if you don't have the value, you can take those individual sample sizes times their averages, add them up, and divide by the total number of terms. Just a little trick if they don't give that to you directly. So I've done all the scratch work that I'm going to do. I'm just going to get into the heart of the problem now. Step 2, I'm going to choose to use an F distribution for my model. And I'm going to start by finding the variation between groups. And the way I find the variation between the groups is I take my individual averages, 2.86 and 3.16, and I compare these to the overall average of 3.04. I have two groups, so my degree of freedom is going to be 2 minus 1. And I need to weight these things by how often they show up. This first thing is 20 important. This second thing is 30 important. I've taken my sample sizes, multiplied by my averages minus the overall average. I squared it, and I divided this by the number of groups minus 1. When I type this into a calculator, I end up getting a variation between the groups of 1.08. So I have used up 1.08 units of variation. I don't know if that's a lot or a little because I don't know how much I was allowed to take. I don't know what my bank account looked like. So let's find the variation within. This is my bank account. So to do this, I'm going to take the sum of each of the degrees of freedom times those variances divided by the total number of terms minus the number of groups. My first degree of freedom is 19 with a variance of 1.4 squared. I'm squaring the standard deviation. Second group, this was out of 30 samples, so that had a degree of freedom of 29. That variance is 1.6 squared. The bottom, I have 50 take away 2 groups. I should get 48. Another way to see 48, I have 19 plus 29. 19 plus 29 gives me a total of 48 as that denominator. I'm going to type this into a calculator. For the var within, I end up getting 2.3225. This is looking pretty good, except for me slashing through that number. 2.3225, that's my allowance. I have that much money in the bank, and I spend $1.08 of that. I'm using way less spread than I'm allowed to take. This seems like a fair thing to me. If it's fair, I'm probably going to fail to reject the null hypothesis. I don't have evidence of seeing something being unfair. Let's see if the test follows that logic, though. I'm going to find my test statistic. I'm going to find my F ratio, or my F stat. And I'm going to find the F by taking the variation between, and I'm going to divide this by the variation stuck within the fraction. That's how I remember it. 1.08 over 2.3225. I'm wondering roughly how much have I taken. And I've used up roughly 46.5% of my variation. I've not used all of my variation left. I still have stuff to spare. So when I find this p-value, it's probably going to be fairly large. P-value, FCDF, I start at 0.465, comma, this is a right-tailed test, so it goes on to infinity, comma, my first degree of freedom, my first denominator was this 2 minus 1 number, 1, comma, my next number is 50 minus 2, my second degree of freedom was 48. I'm typing this into a calculator and I'm seeing what I get. I'm going second, vars, I'm going FCDF, I have 0.465, infinity, 1, and 48. And I get a p-value of 0.499 or so. Let me make that an approximate symbol. So I have a p-value of almost 50%. That's massive. Four-step conclusion. My p-value is bigger than my alpha. I failed to reject the null hypothesis. No evidence, ... of a difference between the groups. So I do not have evidence that there's a difference in GPA between the daytime and evening students. If I were to do the same thing using a t-test, and try doing the same thing with the t-test here, I think you'll find that you get a comparable p-value for the bottom of that process. What I'd be really curious in is how does this t-score compare to the F ratio that we just calculated? This is one of several things that we'll figure out when we're looking at lesson 12, day 2. Another thing that we'll figure out when we're looking at lesson 12, day 2 is some more of the vocab that gets used. Some people say stuff like mean square of the treatment and mean square of the error. I want to understand exactly what those things are talking about and how that matches up to what we've done so far. So we are halfway through lesson 12. I look forward to finishing this up with you next time.